So the point of my lectures, in some sense, is to take all the previous stuff that's been talked about, especially regarding applications of o-minimality in complex analysis, and apply them to geometry, or at least a very particular part of geometry known as Hodge theory. So what we're really going to be studying are periods in Hodge structures. So to motivate the kinds of functions and the kinds of maps we're going to want to apply o-minimality to, let's start by looking geometrically. So suppose that X is an algebraic variety. And to make life simple, let's make X a smooth projective variety. And not doing anything fancy, just working over the complex numbers. Sorry, just adjusting to the setup still. I'll get used to it very shortly. Then there's a bunch of different structures in X that are present. So on the one hand, we have Betty cohomology. So we have usual sort of singular cohomology HNXZ for any natural number n. And so we have this lattice, which by itself tells us very little. Then we also have the round cohomology. H and the realm of X, which we think of very explicitly as closed n-forms modulo exact n-forms. And we have an isomorphism between these two. So if we look at H and XC, this is naturally isomorphic to Hn, the realm X. And what's the isomorphism? Just to get super explicit, well, this side is singular cohomology classes. So essentially, given a closed manifold inside here, the class of one, we have to give a number on it, we have a functional on such things. This side gives us closed n-forms, mod exact n-forms. And so the map is you sort of take the class of omega here, and you map it to the cohomology class, which sends the cycle gamma to the integral of omega under gamma. So essentially, this isomorphism here, what I want to point out is, first of all, it's given by periods. It's given by integration of forms along cycles, which is the second thing I want to point out is that it's very transcendental looking at the very least. It doesn't mean much yet, but it will in a moment. Okay, so far we've only used the manifold structure on X, not the holomorphic structure. So we can bring in some more information with the Hodge decomposition. So when X is given in this form, you can show there is a natural decomposition of the Durham cohomology of X. I guess, well, I'll say naturally isomorphic to a direct sum. Now you go over sums of natural numbers, P and Q, that make up this N. Everything is visible, right? The whole blackboard. Just okay. Of what we call H PQ of X. And what is this HPQ of X? Well, what this is here is closed PQ forms. I'm going to define it just closed PQ forms, not exact PQ forms. We're now, what is a PQ form? Well, essentially, because we have a holomorphic structure, we have purely holomorphic parts, so things of the form dz, and we have anti-holomorphic coordinates of the form dz bar. Right. So essentially, what's happening here for this thing here is that if we look at the tangent space, now it's bad. Cool, cool. This is still okay.
Yeah.
Cool. I'll just stop here. Thank you. And then go over here. If we look at the tangent space of X, the real sort of tangent, the real tangent space stands for the complex numbers. This breaks up into the holomorphic part. Direct sum the anti-holomorphic part, which concretely, this, if we have like coordinates z1 through zm on X, then T1, 0 is the span of dz1 through dzm, and T0, 1, shouldn't have made my brackets ahead of time, is the span of things like dz1 bar and dzm bar. So the holomorphic and anti-holomorphic parts. And now we can take wedge powers. So if we take the nth wedge of this thing over here, we get this direct sum of the pth wedge of this space tensor the qth wedge of this space. And this is exactly our decomposition into PQ forms for various P's and Q's. So if we're just talking about H1, we have holomorphic forms, or sorry, 1,0 forms, which is something times one of these DZIs, and and 0,1 forms, which is some function times these DZI bars. And then if we go to 2 forms, we can tensor 2 of these, or 1 of these and 1 of these, or 2 of these, and so on and so forth. Okay, so that's a local decomposition. It's far from clear that if you do something like this, then it in fact descends down to the level of cohomology in a way that sort of makes sense. But in fact, we do have this relation. Okay. So now this in fact gives us a lot of structure. This here gave us no structure. Well, no structure in the sense that if I give you X and I just record the information of this lattice, this vector space, and this isomorphism, that by itself holds no moduli, it holds no data. But if I then furthermore give you this splitting here, that's already a lot of data. Because now what we have is we have a lattice. We can take that lattice tensor C and get a vector space. That's so far unimpressive. But now what we can do is within that vector space, give us certain subspaces. And now then the data of those subspaces together with the lattice holds a lot of information all of a sudden. So to give a concrete example of this, which will sort of be a running example for us, even at this point, let's take X to be an elliptic curve. Or let's call it E, I guess. I'm not going to be beholden to my original letter. Let's take E to be an elliptic curve. And we'll just study the case of n equals 1, right? So what we can do is we can identify the complex points of E, or maybe you already think, you can think of E as a complex variety or as a scheme, and these are its complex points. I'm not going to be very pedantic about that, at least for now. Let's identify a C modulo a lattice, where a lattice is the span of two complex numbers, 1 and tau. And let's figure out what's going on here. Well, if we look at H10, so what do we want? We want the closed 1,0 form. So naturally, we already have one. If we let Z be the coordinate here, then dz is precisely such a closed 1,0 form. And likewise, H01, we want the closed 0,1 form, is going to be the span of dz bar. And I'm just trying to see how it fits into our decomposition here, right? So lambda is 1 in tau. So what we can do is we can naturally identify the homology of E as sort of the span of 1 and the span of tau. So the span of, let's call them E1 or E2, where E1 corresponds to this 1 here, and E2 corresponds to this tau. And then in this basis, we have the dual lattice, E1 dual and E2 dual. If I write here, it's okay, right? It's just here because of the desk. Great. I have a, E1 dual and E2 dual. So I want to get very explicit about what's going on. I should write coefficients in C here, of course. Oh, this is, no, I should write coefficients in Z here. And of course, I can move to C if I like. Okay, so now what is this isomorphism? Well, once again, let's take a form and see what it does on each cycle. So if we look at the isomorphism from de Rham cohomology to Betty cohomology, and we look at the image of dz, the class of dz maps to, well, if we integrate it along E1, we just get 1. And if we integrate it along E2, we just get tau. So we get E1 dual plus tau, E2 dual. And dz bar is just the complex conjugate. So this maps to E1 dual minus tau E2 dual, right? Okay, now once again, this is information, because if we only had H1E with complex coefficients, this would be nothing. I would just be giving you a two-dimensional complex vector space together with two subspaces of it. There's no information there. All such structures are isomorphic. But we have the integral structure. And so we have a lot of information. In particular, we can recover our original curve sort of purely abstractly from this information. And so how do we do that? Covering E from its Hodge structure, which I know I haven't fully defined yet, but I will. What we can do is the following. We can look at the complex points, or actually the entire, you can even record the group structure here if you want. And what you can do is the following. You can look at the two-dimensional vector space, H1 EC. You can then mod out by the image. I should be writing isomorphisms here, but I'm being a little lazy. Of H10 of E. So far, this is just a two-dimensional vector space mod a one-dimensional vector space. It was just a single copy of C. And so now I want to mod out by this lattice lambda, but I have a natural lattice, which is this thing with integer coefficients. I'm going to mod out by that as well. Right? And so if I look at just this quotient so far without the lattice, that's spanned just by, for example, E1 dual. It's just so EC is spanned by E1 dual and sorry, H1 EC is spanned by E1 dual and E2 dual with complex coefficients. If I mod it by H10, that mods out by this vector over here. And then I'm further modding out by E1 dual and E2 dual, but only with complex, only with integer coefficients. So if I look at the integer multiples or the complex multiples of E1 dual that I'm getting rid of, I'm getting rid of E1 dual itself. And then I'm getting rid of E2 dual. And E1 dual is tau times E2 dual. And so what I recover here is the elliptic curve itself. And the point I want to make is that I recovered it purely from this kind of like Hodge theoretic consideration, where I record this abstract lattice, and I record the decomposition of the lattice tensor C, the vector space, into these subvector spaces. Okay, sorry if I'm beating a dead horse a little bit. But this is the motivation behind studying sort of so-called Hodge structures. We're taking something nonlinear, we're taking this algebraic variety. It might be a nice algebraic variety, but we want to get something sort of much simpler, which we can still study and record a lot of information about it. And so this is the kind of thing that Hodge theory suggests we study. Cool. So this is our motivation. Of course, elliptic curves are the simplest possible case. It gets more complicated, but nonetheless, you can often record a lot of information. Let's define what a Hodge structure is in general. So a Hodge structure of weight n is the following data. So first of all, we have a lattice L. So in other words, this is just a free abelian group of finite rank. A free, I guess, abelian group that's also finitely generated. Just a copy of z to the power of something. And then a decomposition where we look at L, we tensor it with C, and we want to decompose this, or just equals a direct sum of these LPQs, where these are sub-vector spaces. Such that, this part's important, we haven't discussed yet. If you look at LPQ and you take its complex conjugate, what do you get? Well, you just get LQP, which is going to be satisfied here, because if I take a PQ form and it's closed, I take its conjugate, it's still going to be closed. But now the holomorphic and anti-holomorphic parts will switch places. The DZs become DZ bars and vice versa. So from a PQ form, I get a QP form.
Is L dimension rank n or
No. So great question. So far this n is only appearing here. So the L can be an arbitrary dimension.
L could be just one dimension or two dimensions?
Yes, L could be any dimension, and n could be any dimension. And sorry, n could be any natural number so far. So for this algebraic variety, I never specified its dimension. We can still study this for any n. Of course, as we'll see, it's going to be most interesting when n is the cohomology of X most of the time, but you can still do this for any n. Okay, so excuse me. That's the data of a Hodge structure. And most of the time, we're going to care about polarized Hodge structures. So a polarization is a bilinear form Q on L. So it's a It's a map from L cross L to Z, such that so Q satisfies some properties. First of all, Q is going to be symmetric when n is even and anti-symmetric when n is odd. So Q of UV. Actually, I probably shouldn't use UV because my U's and V's look similar. Let me use V and W. Q of VW is -1 to the n Q of WV. Second of all, we want this decomposition to be, I guess, orthogonal with respect to the polarization. So if I look at Q of V and W, well, sorry. If I have V and W are both pure, so V is in some LPQ and W is in some LP prime Q prime, then Q of VW is going to be 0 unless P equals Q prime, and consequently Q is equal to P prime. So unless they sort of sum to n. And finally, these conditions will be justified in a second when we study the geometric case. The final condition we want, and this is sort of one of the more subtle conditions, positivity, is that if we look at V inside L of PQ, then I to the, which is not 0, V not equal to 0 inside of L of PQ. Then there's a positivity with an appropriate sign. I look at I to the P minus Q, times Q of V, V bar. This should be at least 0. And now let me just check that I haven't messed it up, because I always do. Yes, that's correct. Okay. So this data for us determines a polarized Hodge structure of weight n. And this is sort of the fundamental object in the study of Hodge theory. So one thing I want to point out for sort of a little bit later, before I give the main example of where these things come from, is that Hodge structures are in effect built out of periods, right? They're given by taking sort of forms, integrating along cycles. But then we also put the periods together in a certain way so as to sort of remove all choice from it. The data of this Hodge structure and the way we're presenting it, as you can see over here, I haven't told you about the form yet, but I will in a second, depends only on the smooth projective variety X, in fact, only on its holomorphic structure. And so that will make it particularly amenable to studying it in families and getting nice properties, even though when we finally turn to using o-minimality to study it, we'll be able to say something about general periods in families as well. But for now, we'll sort of focus on these cleaner objects. Yes? Yeah. This one here? Yeah. Sorry, what's your question? Oh, it's the square root of -1. Yeah, sorry, it's not an index. It's just I. Are you asking? Yeah, so P and Q are integers. And so I to the P minus, so this is going to be like I minus I, 1 or -1.
Yeah. So the difference between Q and P is not.
Oh, yeah, but sorry, but these LPQs, I understand your question. So you're asking if this is an integer valued thing. Yeah, it's for V that are pure in LPQs, and these LPQs are typically not going to be defined not only over the integers, but not even over the reals. This is a complex decomposition, I tensored with C. And so even though Q started life as a form valued on this lattice, which takes values in Z, once I go to complex vectors, of course, I'm going to take complex values. Absolutely. Other questions? Okay. Cool. So let me keep this board up for a second, because I want to explain where this polarization comes from and what's going on here in general. So let's stick with the setup of X being a smooth projective variety.
Now I also have a question.
Oh, yeah, sure.
Because Q takes integer values, so P minus Q has to be even for this to be possible.
Sorry, again, Q takes integer values on the lattice L.
Oh, yeah, yeah.
But once I tensor the complex numbers, it's a free-for-all.
Okay.
Yeah, absolutely. Okay, so one other thing we haven't used yet is the projective structure of X. So far, we haven't used algebraic structure at all, but we haven't used the projective structure. So we have this class. We have this, first of all, line bundle, O1 on X, just a class of a hyperplane section. And we're just going to care about its first Chern class. So this is just going to be some element in H2 of X. And it turns out that for a smooth projective variety X, you actually, well, shouldn't study the full cohomology, because the full cohomology does not admit a polarized Hodge structure. Instead, what you should do is define the primitive part of the cohomology of X, which you can define on Z, or maybe I'll define it on C right away. Doesn't matter. And again, I want to make sure that I don't get this wrong. Well, let me first say what this is. So the primitive cohomology of X will be a subspace of the full cohomology. And it's going to end up being a subspace such that if we want to look at the full cohomology of X, it's going to be the direct sum over k at least 0 of the n minus 2kth primitive part of X. So this is something inside the n minus 2kth cohomology. So to get it up to the nth cohomology, we're just going to cup it with the first Chern class of O1 to the power of k. We're going to get a decomposition like this, which now is going to depend very much on our first Chern class. Okay, so now I haven't defined this yet. What is it going to be? Well, before defining it, let me define what our form Q is. Our form Q what is it going to be? Well, it's going to be defined the following way. If I take Q of alpha beta, I'm going to define it to be alpha cup beta. And then I'm going to further cup with C1 of O1 the dimension X minus N. So this gets me inside the 2-dimension X cohomology class, top cohomology of X. So this is something inside H 2-dim X of X. And this here is naturally isomorphic. So in fact, if I started with Z classes, I can put a Z here. This is naturally isomorphic to Z. So if I have middle cohomology here, if n is dimension x, I just take these two cycles and I intersect them, essentially. And that's how I get a number. Otherwise, I cup them together, and then I cup together with as much of C101 as I need to in order to get myself up to top dimension here. That'll give me a number. This, by the way, has a very nice interpretation in terms of forms. I shouldn't have used this backboard. Let me switch to start using this one here. This is a very nice interpretation in terms of forms. So if I let omega be a form whose class, using equality here is a bit of a shorthand of a natural isomorphism, but let omega be sort of a Kähler form, like pulled back from the Fabini-Studi form or something, a projective space, but some closed form whose cohomology class represents the first Chern class. Then if I look at Q of alpha and beta, if now alpha and beta are also forms, sort of closed differential forms, and I translate via the isomorphism, and what I get is the integral over x of alpha wedge beta wedge this omega to the power of dimension x minus n. So this is if alpha and beta are inside the Ram cohomology of x. I translate it this way. Okay, so now, given that we have this definition, we can simply, so what is the primitive part finally? We can finally define the primitive part inductively. So we just define Hn prim of x is defined to be the perp to what it should be defined as. So we define it such that this direct subdecomposition we want to get is actually an orthogonal decomposition. Okay, and it turns out with this definition, if we let L be the integer part, the lattice, which is the primitive cohomology of X, then we get an actual polarized Hodge structure. Questions about the definition? I'll say a little bit more, but okay. So the only two sort of takeaways are, first of all, it depends on the actual projective structure of X. If I give you a, this rarely comes up in practice, but if I give you a smooth algebraic variety, that's not enough to specify this Hodge structure. I have to give you an actual choice of ample line bundle, or like embedding into projective space, or this H2 class, however you want to think about it, in order to give the definition. And the other thing I want to say is, what is the reason we have to do this? What if you were sort of like, well, this seems silly. Let's just use the entire cohomology of X. Let's use this form Q, bada boom, we're done. What goes wrong? What goes wrong is something a little bit subtle, is this positivity here. And it doesn't go super wrong. You will still get this property. Everything will still be non-negative pairings. And why is that? That's simply because of this formula here. If I take a PQ form and I wedge it with its conjugate, the sort of function part, the coefficient part, will just be a norm squared. That's a positive thing. Everything else will group up as DZs, wedge DZ bars. Those are sort of locally positive. So I'm never going to get anything negative. Nonetheless, the way they pair up together could still give me 0. Okay, so what's in my opinion, here is a helpful example of what goes on. Just to convince you this primitive thing, even though it's a bit annoying, it's necessary. So y primitive so as an example, let x be not the elliptic curve from before, but something pretty similar. Let's let x be E cross E. And let's let n equals 2. Let's consider h2 of x. So h2 of x, let's even look with z coefficients. We can use Kuhn's theorem, which works very well here. So what is it built out of? Well, it's built out of h0 of E tensor h2 of E plus h1 of E tensor h1 of E plus h2 of E tensor h0 of E. Right? And so we see here that automatically something wrong happens. If we look at the de Rham H2, so this is isomorphic canonically to H2 de Rham. So which two form corresponds to what's happening here? Well, we just take a top two form on the sort of second coordinate E and just pull it back over here. So this is like what this corresponds to is the class of the pullback under projection to the second coordinate of omega, where now omega is essentially a top two form or a two form on E. In our previous coordinates, it could be like dz where dz bar or whatever. But the point is, if I now take this form and I wedge it with its conjugate, I'm obviously going to get 0 because it's only supported in the second elliptic curve. Second elliptic curve is a two-dimensional real manifold. It can't support a 4 form. And so positivity breaks down. And so again, we get non-negativity, but we get the sort of degenerate part. And if we put in the primitivity conditions, that's going to go away. That's why we have to worry about this kind of annoying primitive thing. Okay. So that's the Hodge structure of a smooth projective variety. Okay, so far for every smooth algebraic variety, we just get some information. It's interesting information, but it's just a collection of just some finite data, some collection of numbers. So obviously the interesting thing we're going to want to do is we're going to want to study Hodge structures and families. Actually, sorry, I should mention one more thing first. We're going to want to study Hodge structures and families. Let me mention one thing first, because it's center of the subject, of course, which is the Hodge conjecture. One reason Hodge structures are super interesting. Okay, so given this sort of structure, a smooth projective variety, we have all this data. Now, suppose we're in that situation up there. And suppose we have inside X this Y, which is an algebraic subvariety of some dimension K. This is not a rare thing. Varieties have many subvarieties. Just do it locally, close it up. Happens all the time. Okay, but if you have this kind of thing showing up, Then what you can do is you can look at the induced cohomology class. So we get a class Y inside the let me say it got codimension k, because it'll make things simpler. We get the class Y inside the 2kth homology class in Z. Why is that? Well, Y is a manifold with a natural orientation given by its complex structure. It might have singularity, but that's not going to mess up the existence of this thing. You can do this even if it's singular. We get some class Y inside here. However, something very cool happens because Y is a holomorphic submanifold. So if we look at a differential form on Y, which is pure of type PQ, so we get P holomorphic parts and Q anti-holomorphic parts, and P plus Q is equal to 2K, the only way for that to be not zero is for P to be K and Q to be K. Just like if I take a 2 form on a curve, it's not zero, it simply has to be a 1-1 form. There's no choice because, well, that's gone already. But you sort of have to use everything you have just to build up a 2K form. This automatically is not just here, but it's inside HKK of X. So again, why is this true? Because if I take a form and I want to understand its intersection with the class Y, what I do is just restrict it to Y and I integrate. Now X has lots of interesting forms of type 2K. We have a form of type 2K and Y. The only way for it to be not zero is if it's actually type KK. So automatically this is inside here, and that makes this what's called a Hodge class. And these are very rare, simply because this is a lattice, and this is a proper vector subspace. So they have no reason to intersect sort of generically. It's a big coincidence if these two things intersect. And so the Hodge conjecture is that all Hodge classes come from algebraic subvarieties or cycles in this way. Yes?
I don't understand why this lies in the integral value.
Oh, why it lies inside here? Just because Y is an integral manifold. So what is the, so again, how do we get it inside here? Well, naturally, this is a homology class because it's a submanifold. And to get it to be a cohomology class, we need to use Poincare duality. So given any other class, we just intersect them and we get something inside here. Now we'll get finitely, because they're both actual manifolds, we'll sort of get some finite number of points, and that'll give us sort of the I'm sorry?
Why it's in the value?
Well, so again, the question is how do you view this inside here? And the way the isomorphism works is, so what is this thing? It's singular cohomology. So if I pick a basis of make sense? Okay, great. Of course, if you check, all the isomorphisms are compatible, but that's all sort of standard, which is code for I haven't done it, but I believe it's people who did. Okay, so this conjecture is sort of very interesting, and it's kind of, if you're a number theorist, it's analogous to sort of the question of finding rational points on varieties, and you want to find them using some kind of linear data, maybe looking at Galois representations or something like this. It's similar here. Of course, if you're just looking for sort of algebraic subvarieties, those are aplenty, because you can just make them sort of locally. So there's many, many algebraic subvarieties. So the sort of one natural question to ask, if you want some sort of analog, is, well, which cohomology class are represented by algebraic subvarieties? Because if you look at subvarieties sort of as coming in families, the cohomology classes don't change. So this is sort of a very nice kind of transcendental condition you can put on. And then if you were to prove this Hodge conjecture, then in some sense, you could produce cycles or verify their existence just by looking at cohomological data. And that's very appealing. From what I understand, so it's very unclear if this should be true. I mean, the experts seem like they're kind of torn on it, but at the very least, it's an extremely interesting question. Okay, extremely interesting question and a very motivating one. There's typically a break taken, right? No, people go for 2 hours straight. Why don't we take I don't know, what's reasonable? 10-minute break, great. Yeah, let's come back at 10:05 and resume. A good place to stop.
The Hodge class started also before that happened. Then you can say that a lot of these you could actually isolate it. But for the concrete cases, you can just find the line.
How about this? Oh, it was muted. Okay. Perfect. Excuse me. All right. So now that we have the sort of basics of Hodge theory, let's start by studying these things in families, where we can start bringing some relations to o-minimality to bear. Okay, so what do we mean by studying them in families? Well, what you can do is you can look at a family of algebraic varieties over some other algebraic variety, which we'll eventually do. But for now, let's assume we just have a family over a disk. So let me say like X mapping to a disk be a family of smooth projective varieties. Where our disk here is just the sort of, this is the ball I don't know, the ball of radius 1 around 0 or something. This is more notation than it's worth. I'll just write it down. Some small ball. You have a holomorphic family of smooth projective varieties. You can define it in any number of ways. You can just give sort of equations whose coefficients are holomorphic functions inside D, or a variety of other ways. You can give a map from D to some Hilbert space. It doesn't matter. So suppose you have this kind of structure. Well, since you're over a disk and a disk is simply connected, one thing you can do in this case is, we can trivialize. Let me call this phi or pi. We can trivialize the cohomology of the fibers x sub t z, which is in the disk. So we can pick sort of global coordinates for the cohomology classes of the fibers, because D is simply connected. And now, essentially, by looking at Plucker coordinates, we can actually get functions out of our Hodge theory. So by taking Plucker coordinates for the sort of HPQs of the fibers of these x sub t as t varies, we get functions, holomorphic, or just functions for now, on our base D. Getting low again. Let me raise it up. Thank you. So, as a simple example, if, for example, dimension of, let's say, h n0 of these x sub t's is 1. By the way, it's not totally obvious that these x sub t's, the dimension of these HPQs don't change as you move in the family, but it's broadly true. If the dimension of this is 1, what does this mean? This means there's one-dimensional space of like a top holomorphic form, or sorry, a holomorphic n form. We may let sort of omega sub t be a holomorphic n form on x sub t. We can let this vary in some nice way, perhaps even holomorphically. And then if we have some gamma is a class in Hn of, let's say, x0z, which is canonically the same as Hn of xtz, we can study the map. T goes to the integral over gamma of omega t, and this is some function on x. Sorry, I'm getting low again. Let me write the next board. I apologize. So if we have that kind of setup, we may study the map. T goes to the integral gamma of omega sub t. So this is just a regular period which we're studying. We have this varying form omega sub t. We have the trivialized cohomology class, which you can move in families because we just care about the integral cohomology. And sort of locally, these x sub t's are all morphic to each other, so we can identify all of their cohomologies. And we can study this thing, but of course, this depends on sort of how we normalize omega sub t, depends on the choice of gamma. And so more canonically, what we actually end up studying in this case, the sort of data that's intrinsic to the Hodge structure, intrinsic to X. If we pick a basis, gamma 1 through gamma n is a basis for Hn x0z, canonically isomorphic again to Hn of these xtz's. We may study the map T goes to all of these integrals, gamma sub z, gamma sub 1, omega sub t through gamma sub m, omega sub t. And we think of, I should probably change the brackets. And we think of this point as an element m-1 dimensional complex projective space. And now this is canonical. It doesn't depend on which form omega sub t we picked. It was one dimensional, so we had the choice of scaling at every t. But that'll cancel out once you projectivize because you get the same scaling factor in each one. Okay? And so this is a simple case because in this case we get an actual point inside projective space. In general, though, you will get a point not in projective space, but inside some Grassmannian, depending on the dimension of Hn0, or whichever HPQ you happen to be looking at. Great, so now we have these sort of maps, and now we can study these maps as we vary. Okay, so that's kind of the local picture in terms of what's going on. We're studying essentially periods and families. But by only recording certain ratios of the periods, we're making our life easier because we're studying canonical information. All the sort of choices that we would otherwise make are taken out of the picture. So let's make this a little more formal. And we'll come back to the example of an elliptic curve, of elliptic curves, to sort of ground ourselves to see what's happening concretely. And for that, we need the notion of a moduli space of Hodge structures. So sort of as Hodge structures vary, what sort of set do they vary in? Well, let's remember what a Hodge structure is. We're given a lattice, and we're given a quadratic form on that lattice, if we want the polarization, which we always will. That's discrete data. That doesn't move continuously, because those are both z datas. And then we're also given these HK decompositions, which are continuous. And so those are the things we want to let vary. So let fix our sort of lattice L together with our quadratic form Q, our bilinear form Q on L. Then we let D check be the space of all decompositions of LC into a direct sum of these LPQs, such that Q of LPQ, LP prime Q prime is 0 if Q is not equal to P prime. And LPQ is equal to LQP bar. So we could try to do something like this, right? Let me put a wrong here. This is not what we're going to end up doing for a couple of different reasons. But we could try doing something like this. So this is not very natural for two different reasons. I guess they're related to the same reason. The first one is that this condition here, that LPQ is LQP bar, is sort of not great because we want things eventually to be holomorphic, and convex conjugation is gonna screw that up. So we don't want this. Moreover, if we just look at the simple case of elliptic curves, we'll get L is a two-dimensional thing, and this is just recording sort of vector subspaces inside there, such that them plus their conjugate is the whole two-dimensional vector space. That's going to be not all of P1, but it's going to be P1 minus the real part. You're sort of going to manually exclude real lines because real lines are their own conjugates, and so they won't give you this kind of span. So this is bad for a couple of different reasons, both related to complex conjugation. So how do we fix it? You also notice I'm ignoring positivity, but that's something that is not bad. That's something we'll keep till the end. Okay, so going from direct sum decomposition to filtrations. I realize this lecture has a lot of like linear algebra kind of nonsense that we're doing. It will vanish starting with the next lecture. We focus a lot more on the o-minimality, but this is sort of important background for setting things up right. So I ask you to bear with me just for a little bit longer. Direct sums and filtrations. So this is a very unintuitive step, at least to me. It took me, before I was doing Hodge theory, I kept watching lectures, people kept doing filtrations, I never understood why. So let me try to motivate why we're doing filtrations in a way that's hopefully clear. So instead of recording this direct sum decomposition, we're going to define FPX. Again, I want to make sure I'm compatible with Wikipedia. Doop, doop, doop. To be the direct sum over J, let me write it this way, P prime at least P of H P prime, sorry, not X, FPL, excuse me, I'm getting this mixed up. Let FPL be the direct sum of P prime at least P of L P prime Q prime. Okay, so this is a descending filtration. We have L is equal LC, I guess, is equal to F naught L, which is everything. All the P primes are at least bigger than this. And then it descends F1 L all the way through Fn L. And there's no Fn plus 1. Fn plus 1 is just 0 for weight n. Okay, so if we have this direct sum data, we can get this filtration. And we're actually going to keep track of the filtration instead of direct sum decomposition, which feels a little counterintuitive again, because direct sums are much nicer than filtrations. Let me first convince you that we're not losing anything. Once we have this filtration, we can actually recover the direct sum decomposition. Why is that? Well, it's very simple. If we look at FPL bar, we're inside a complex vector space with a real structure, in fact, a rational structure, so we can conjugate. What's that? Well, it's a direct sum over P prime, at least P, of L, Q prime, P prime. And let me just flip things a little bit. Direct sum of P prime most n minus P of L, P prime, Q prime, because these two sum to n. So if I just reindex, I get this kind of thing. In other words, if I look at FPL and I intersect with Fn minus PL conjugate, what I get is just LPQ. Right, so we have these LPQs, the FPLs are the direct sums taken from the left, the conjugates are from the right, so if I intersect them in the right way, I recover these. Okay, so from direct sum decomposition, from the filtration, we can recover the direct sum decomposition, so it can't be that much worse to keep track of it. Now, what about our conditions with respect to Q? What about our conditions? I want to point out also that if we start with the filtration and define this to be LPQ, then this complex conjugacy condition is tautologically true. Because if we complex conjugate this, we just flip the P and n minus P. So this would be fine. Great. Now, what about this condition here, that this is 0 if Q is not P prime? Well, we can record this isotropic condition by saying that Q of FPL, let me say FAL, FBL is supposed to be 0 if A plus B is bigger than n, because we need these two to sum to sort of n, and so we have to go far enough away on the right or on the left in order to make this true. If A plus B is bigger than n, that's right, that makes sense. Okay, so we can record these conditions very nicely in terms of the filtrations. So what's the point of the filtration? Well, it solves at least some of the issues we've been dealing with. So this doesn't work for the reasons that I was saying. Now we can actually define D check to be the space of filtrations, to be the Grossmannian, or flag variety, whatever, of descending filtrations as above. Satisfying this condition star. So it's nice for a couple of reasons. One is we no longer have any complex conjugation. If we want to recover the direct sum decomposition, then sure, we talk about complex conjugation. But as long as we don't care about recovering that, everything is complex linear. This condition here, together with the space of filtrations. As a result, or I guess secondly, we don't leave anything out. This is an actual Grossmannian. It's a, it's a projective complex variety. So it's a nicer space. Another thing that's going to be nice is that because there's no complex conjugation, this D check naturally has a holomorphic structure. So we can hope for maps and families to be actually holomorphic, for Hodge and families to be holomorphic. This is something I never clued on to, that, or for a long time I didn't clue on to, that if you look at these Hodge decompositions, these HPQ decompositions, the very last bit is the holomorphic bit, right? HN0 is you take holomorphic forms, you integrate them along cycles, you get some numbers, you record those numbers. That's kind of obviously going to be holomorphic in families. But if you move to the other HPQ pieces, those aren't holomorphic in families. And in fact, they can't possibly be because HPQ is HQP bar. So if one were holomorphic, the other would have to be anti-holomorphic. So these start mixing up in sort of all sorts of weird ways. In order to make it holomorphic, we instead switch to this filtration data. And that's actually going to be holomorphic. Okay, I don't know if that's the best motivation, but hopefully it gives you some sense of why this filtration is a nice thing to keep track of, even though it loses this very nice direct sum interpretation we had before. Okay, so let D check be Grassmannian the filtration satisfying this. In the case of elliptic curves, this D check is just P1, is just a one-dimensional subspace inside of a two-dimensional symplectic space. The isotropic condition means your line is isotropic, which is no condition at all. And so we just have a line in two-dimensional vector space, that's P1. Okay, now we need more than that. We need the positivity condition. So now let D inside D check be the open subset. Not trivial that it's open, but it's not too hard to show it's open. Where the LPQs satisfy the positivity condition. That if we take something inside there and we wedge and we take Q of that with its complex conjugate, you get something times the right sign. Yes.
And the number n is fixed.
Yes.
D check depends on n.
Yes, I'm sorry. So they depend on n, and they also depend on L and Q, right? So there's a lot of. Yes, yes, yes. I'm fixing an L. The way I'm trying to make a moduli space is I'm first fixing the L and Q. I'm letting the filtration vary.
Oh, okay.
Absolutely. Thank you. Yeah, there's a lot of dependencies that are sort of going to be left out because they're annoying to keep track of, but you're 100% right. So for example, one thing that's important also is like, what is the discriminant of Q? If I change the discriminant of Q, I get a whole different sort of D and D check picture going on. There's a lot of combinatorial data here. Okay, so in the case of elliptic curves, this is P1, and this here is going to end up being the upper half plane. Okay. Okay, so then if I give you a Hodge structure with a basis, I get an element of this D. So if I am in this context here, where I have a smooth projective variety over, say, an open disk, and I've trivialized the cohomology, I've picked the basis for the cohomology, which I can do over a disk. Then I get this L, I get this Q, and I get this well-defined map. Okay. In general, if I have my X defined not over a disk, which it typically won't be, but over some other algebraic variety, say an elliptic curve or whatever else, then I'm going to have monodromy. And if I go around the loop and I do this procedure, I'm going to get some automorphism of this LQ thing going on. So my LQ is not based. So in general, when something is not based, we have to mod out by the automorphism group. So now in this case, you can let G be the group, which is the automorphism group of LQ. I'll write it this way to be able to think of it as a group scheme. So we can think of its values over Z, over C, over R, over whatever sort of base you want. But more importantly for now is the Z points of it. So then the period space so-called period space is defined to be this D mod G of Z. And so now finally we have some sort of well-defined moduli space. Now, finally, suppose we have a map from X to S, be a smooth map of projective varieties over, let's say, over a complex manifold. That's not necessary, but let's just do that for now. Then we get a well-defined map from this S to this D mod GZ. And this is called the period map. It'll be our basic object of study. Where again, the construction of this D depends on the choice of an N. And of course, it depends on the isomorphism class of the nth primitive cohomology of X together with this form Q. And so what is this map? This map sends a point little s.
Getting low again.
Getting low again. I'm going to switch. So it's going to be OK. Sorry, let me remind myself by doing a little doohickey here. So phi of s is just the class of the nth primitive cohomology of X, fibered over T, as a lattice, together with the corresponding Q and with the corresponding Hodge filtration. The isomorphism class of this triple. Okay. Yes. Now I just want to record a fact, which maybe we'll prove later if we get more into cohomology, but maybe we won't. Fact is this phi is holomorphic. So this is actually, I should attribute this fact to Griffiths, who proved it. Phi is holomorphic. It's not super deep, but it's not trivial either. It's not immediately obvious. Okay. So this is the basic setup. Given a family of smooth projective varieties over some base, you get a corresponding period map from that base to an appropriate moduli space, the so-called period space. And now we can begin to study this map. So again, I've said this already in words, but let me just write it down so that it's super clear. If X is a family of elliptic curves over S, and we take n to be 1, then D check is P1. D is the upper half plane, and G is just as again, not super canonically, but G is just the algebraic group SO2. And so what do we get? In this case, we get a map from S to the upper half plane mod SO2Z. which was talked about earlier, which you can think of as just taking the J invariant, for example, or in some other way. Okay. Just maybe to yeah, maybe just to spell it out, why D is the upper half plane is if I have in this case we have essentially L is spanned by E1 and E2, and Q is the symplectic form. So Q of E1 E2 equals 1, and Q of a vector in itself is 0 because n is odd in this case. So if you flip two things, you get it's negative. The reason D is the upper half plane is if I look at Q of E1 plus tau E2 against its conjugate, E1 plus tau bar E2, and they multiplied by I, which is sort of P minus Q. Or sorry, it should be minus here. I multiplied by I. What I get is what? Well, I get Q of E1 times negative tau bar. So I get minus tau bar here. And then I get plus tau. Sorry, minus tau bar. No, it should be plus. Sorry, I'm sorry. I'm not going to change things again. Okay, so let's see. We get E1, E2, so that's tau bar. We get E2, E1, so that flips to a -1, so we get minus tau. And so if tau is x plus Iy, what we get here is twice y. Never do anything on the board. I think we get twice y. And so the condition is that this is positive, and that translates to y being bigger than 0. So D is naturally the upper half plane with this interpretation. Apologies. Let's see. Okay, good. Okay, so this case is very instructive in some ways, the case of elliptic curves, but it's oversimplified in others. So what's one important way that this is oversimplified? So in this case, if we look at our period space, H mod S to Z, yes, it's a complex manifold, but in fact, it's got an algebraic structure. It's an algebraic curve. It's P1 basically with a couple of weird points. J is a coordinate. And so even though a priori, this is just a holomorphic map, we actually end up getting an algebraic map from, if S is an algebraic variety, from S to H minus S to Z, thought of as an algebraic variety. And that's not surprising. If we have an algebraic family of elliptic curves, the J invariant is also algebraic, and so we expect to get an algebraic map. In general, and I'll say a little bit more about how one can think of this. But in general, our period space, D mod GZ, is very far from algebraic, which I mean it admits no algebraic structure. This is due to a bunch of people. I mean, Griffiths did a bunch of work on this. I don't remember the names right now. I'll come back with references. But in general, this admits no algebraic structure. So sometimes it does, like importantly in the case of Shimura varieties, which are also moduli spaces of certain types of Hodge structures, you get an algebraic structure. But most of the time, if you just pick random lattices and Hodge numbers, you won't. And so you end up being in this very funny situation where you have this complex manifold, sort of a very reasonable complex manifold, and it's not algebraic, but it admits all sort of algebraic data. There's all sorts of maps from algebraic varieties to this complex manifold. Namely, whenever you have any family of algebraic varieties, and they have interesting cohomology, which, okay, is not always the case, but it's very, very frequently the case. Well, I shouldn't say that. There's a lot of important examples. Yeah, you get a lot of examples like this. Then you get maps in some kind of period space, which itself is not algebraic. And so the idea is we want to be able to extract some kind of information, even algebraic information about our algebraic varieties from this sort of object we want to study directly, even though it itself admits no algebraic structure. Okay, so one of our goals, sort of goal one, I guess, yeah, there's basically two goals that I have for this set of lectures. Goal one is to give a definable structure to this object. So give a definable Rnx structure to d mod gz such that, so it turns out actually giving a definable Rnx structure is very, very simple. You can give almost anything an Rnx structure, just take any cover and do some stuff. In practice, that's very, very easy. Of course, you want to give an Rnx structure which has nice properties. And in this case, what are our nice properties? Well, why do we care about the space to begin with? We really care because of these period mappings. And so the goal is to make all these phi's such that period maps are definable. Okay, so that's goal one. Maybe I'll write 3 goals down. So that'll be our first goal. Goal 2 will be to combine goal 1, the result of goal 1, with o-minimal complex analysis, with all the stuff that was talked about, to extract algebraic data. And I think I'll say something about that before. Yeah, today. Remind me, do I go until 10:50 or 11? How do the lectures work? 11?
Without the break, we go to 10:50. So.
You without the, oh, right, okay. So maybe I'll end in a few minutes then. To extract algebraic data. That'll be our sort of second goal. In particular, we will say something about the Hodge conjecture in families using these methods. And then goal 3 is going to be, in some sense, subservient to goal 2 a little bit. But d mod gz is not algebraic. So we have the definable Chow theorem, which is an extremely powerful result. But ultimately, what that used to do is prove that certain things you expect to be algebraic, in fact, are. D mod gz is not. And so, whatever we develop, we're not going to get around that problem. So it turns out that even though d mod gz is not algebraic. We still want to study maps from algebraic varieties to D mod Z. So what can you do in this sort of situation? Well, what you can do is you can still study deformations of algebraic structures inside your non-algebraic but definable complex analytic objects. And so we want to study some kind of robust enough o-minimal complex analysis to accommodate deformation theory. And that's going to help us in our study of goal 2. So I'm being very vague. I know I'll make things a lot more precise. But goal 3 is sort of develop a robust enough o-minimal complex analysis to handle deformation theory. And what that really means is infinitesimals. So it doesn't mean start over at all. We already have a very functional o-minimality and o-minimal complex analysis developed by Peter Zio and Starchenko as well as others. But we want to extend that a little bit to allow us not just to talk about sets, but to talk about things like structure sheaves and non-reduced schemes and stuff like that, in order precisely to be able to talk about deforming algebraic structures inside definable but not algebraic sets, because that's the world we live in. That's sort of all we have. Okay, so broadly speaking, this is what the goal will be of the next 7 lectures. Okay, maybe this is a good place to stop then. Any questions? Yes, please.
So can you recover the X from the stereo map?
That's a great question. Oh, in which case?
In the elliptic curve case.
In the elliptic curve case, you can.
Yeah.
Yeah, because in the elliptic curve case, you actually get the J invariant. The
In the general case?
So in general case, it's complicated. In the most generality, no, you can't. In fact, In fact, there are cases of X's that are interesting with no interesting cohomology. And in that case, this map tells you nothing. You're mapping to a point, basically. But there are a lot of interesting examples of families of X where this is true. So this is referred to as a Torelli theorem in general, after the Torelli theorem for curves. It's like if X is a curve, then yes, you can recover the full curve from its Jacobian, and the Jacobian is the same data as the Hodge structure for n equals 1. Just like we recovered the elliptic curve from the Hodge structure, if you do the same construction for an abelian variety, you recover the abelian variety. If you do it for a curve, you recover its Jacobian. So in that case, the answer is yes. The answer is also yes for smooth hypersurfaces inside projective space. So in many interesting examples, the answer is yes. In general, the answer is no, however. All right, so I'll see everyone on Friday. Thanks.